In this session, we are going to discuss about the B+ trees. We have seen and discussed in the early videos that multi-level indexing is actually, when inverted, results in a form of a search tree. But because the indexes are in ordered manner, insertion and deletion becomes a very big task. Hence, we use B trees. An advancement over B trees is the B+ trees. So, in the earlier videos, I have recorded about the B trees. You can go and see how to create a B tree, how to insert and delete values in the B trees. Today, we are going to discuss about the B+ trees. This is the URL of, let me make, okay. This is the URL of the online tool that can help you visualize how the B+ trees are created, how the elements are inserted and deleted out of it. Okay, so now let's see the difference. Basically, difference when you see a B tree and a B+ tree is given in the slide. If you notice here, the same elements are being created as a B trees in the first one, and the second one is the B+ trees. So I want you to take 1 minute to spot the difference between them. So please see what is the difference between the B tree and and the B+ tree in the appearance. Okay, now I will tell you the B+ trees hold the record pointers, okay, and the data pointers in the leaf node. So what all elements you see here in the tree are actually available in the leaf nodes, and the leaf nodes, also called as the leaf siblings, they are all connected in a linked list fashion. Hence, you see the leaves in the B tree have, for example, in this particular case, 1, 2, 3, 4, 5, 6 elements, whereas the B+ tree will have all 10 elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then both of these trees were constructed with the same number of elements and, in fact, the same values. Okay, now why do we have this plus information? It is actually following the B+ tree is actually a B tree, but with more information inside it, and that is why the plus stands for in B+ tree. Okay, so what is that plus? That plus is saying that these elements, the internal root elements, are available in the leaf node. Okay, so having this available in the leaf nodes makes the insertion more simpler, makes the deletion more simpler, okay, and more spontaneous. This is actually the difference between the B and B+ trees. Okay. And also, if you see here, the middle element in the B tree, for example, is 20. The left child is less than 20, and the right child is greater than 30, greater than 20, which is 30 in our case. Okay. In this particular example. But now, if you see here, we have a root element, parent, internal node. This is called as internal node. This is called as internal node. This is called as the root node, and these are all the leaf nodes. However, this internal node is a parent of element 10 and 20. So if you see here, the left child is lesser than the parent, but however, the right child is equal to the parent. Why? Because we have to store this information, this pointer, uh, inside the leaf node. Okay, and the leaf node is nothing but the child node, and the child node is that is why having the same value what you see here. Similarly, for the 40 element, the left element, the left child is 30, which is less than 40, and the right child is 40 itself. Because we want to save this information, this root information here, okay, in the leaf. And if you see the element six, parent 60 is having the right child as 60. We have here the parent as 90, and one of the leaf node is 90. And here the internal node or the parent node is 80 and the leaf node is 80. So this is how the B+ trees appear, and they bit differ from the B trees because they have this additional information stored in the leaf nodes. Okay, now let's read more about it. Okay. Now, before we, discuss about the B plus trees, I just want to give you some introduction on the B trees. The B trees are balanced. Okay, you see there is a balance. At each level, we have, uniform number of elements. Here we have two, and yeah, sorry, here we have one parent. So it says that there is one root, and at the second level we have the children, at the third level we have the children, and at the fourth level we have the you know children, equal number of children. Or no, yeah, for example, here we have one child, and here also one child but holding two values, so this is possible. Okay, so the balance is maintained when you insert or when you delete, so ensuring that the B plus tree is balanced. We follow certain rules that we will see when we are going to do the construction of a B plus tree. Okay, so node structure, all the now let us understand the node structure. In a B plus tree, all the keys are present in the leaf nodes. All the keys you see, these all keys are available in the leaf nodes. Okay, the internal nodes will contain only keys used for indexing. Okay, these are only the pointers, record pointers. Okay, and this is the actual keys. This design simplifies the structure and the search is much efficient. Sequential access is designed to support range queries and the sequential access. Okay. Since all keys are present in the leaf node and they are connected in the linked list format, traversing or moving is bit easier. And if you see, all the values are sorted, in the ascending order from 10 through 100. Okay. Fan out factor. Okay. So this is the new term. Fan out factor is nothing but the number of children out of a parent. So here the fan out factor is 2, 2, 2. Okay, so the fan out factor is typically higher than in the B tree. Here you have, lesser number of children, and here you see the same elements have been constructed, same elements have been used to construct the B plus tree, and here you have one level, two level, and three level, and here we have one, two, three, four levels. Because we are going to store the internal and the parent nodes in the leaf nodes, it looks much bigger than the B tree. Okay, so the fan out factor, fan out factor is nothing but how many children are coming out of a parent. So here we have, this extra level. That's why is this is the extra level in the B plus tree. The fan out factor is more in the B plus tree, and we know the cause for it. Multiple keys can be stored inside the internal node. Okay, unlike the B trees, where each node has only, um, lesser number of keys. Here we have more keys because we have to store the leaf nodes to hold the internal and the parent node values. Okay. Now, a quick recap about the B plus trees. In a B plus tree, all the pointers to the data records, all the pointers to the records exist in the leaf nodes. A B plus tree can have higher, can have less levels or more levels or higher capacity of search values than corresponding B trees. Actually, this is not less, this is more levels. Okay. So a B plus tree can have more levels or higher capacity of search value than in the corresponding B tree. Yeah, the B tree for these elements is shown here, and it is having lesser levels when compared to the B plus tree for the fact that these internal record pointers are kept in the leaf node also. Okay. Now in a B tree, pointers to the data exist at all levels of the tree. Pointed to the data exists in all levels of the, but in the B plus trees, they exist at the leaf level nodes. Okay, so now let us look into the node structure of the B plus tree. The node structure includes, for example, here we have the left subtree lesser than the parent, lesser than or equal to the parent. Okay, and the middle child lies between the first key and the third key, for example, or in the last key. So this is the middle subtree. The right subtree is always greater than the last key value. And here we have a tree pointer and we have the data. Okay. Now, this is the node structure. Okay. And let us see how is the leaf node looking like. So B is the leaf node of the B plus tree. The leaf node is going to have the key and the pointer, which is connecting it with the next key. For example, like this, the key and the pointer connecting it to the next key. This key and the pointer connecting it to the next key, like a linked list way. Okay. So, and then in the end, we have the pointer to the next node in the tree and keeps on until we reach the last node, like here. Okay. Now let us draw the B plus tree with the given set of values where the order of the tree is 3. Whenever you are being asked to draw a B plus tree, it is very important to know the order of it, so that this order helps you calculate the maximum number of children, which is equal to the degree of it. In this case, 3. Minimum number of children, which is given by the formula p divided by 2. Okay, which and the ceil function applied to it, which is 2. Maximum number of keys is given by the formula p minus 1, which is equal to 2 in this case. Minimum keys is equal to p divided by 2, apply the ceil function to it, minus 1, which is going to give us 1 in this case. Now, before we draw, I want you to try doing this without any knowledge. Just apply the formula for the B tree and try to get these internal nodes in the leaf nodes. Okay, just pause the video for 5-10 minutes and try to draw the B tree for this. Okay, it should look like this one. Okay, and then try to draw the B plus tree. Okay, on your own, considering these conditions. Okay, these conditions. Okay, and then we will do it together. Let's draw the B plus tree being asked in the slide together. The number of the values were 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. The order of the tree given was 3. The order of the key is very important when we are trying to construct the B tree, because it is going to tell us the number of maximum children and maximum key values that can be stored inside a node. So the maximum number of children is always equal to the order of the tree, and the maximum number of keys inside it is always 1 less than the order of the tree, which is 2 in our case. So how is the node of the B plus tree going to look like? It is going to hold 2 values with 3 children. Now let us enter the first value, 10. Let us enter the second value, 20. Okay. And as soon as we try to insert 30, the node will overflow and node split will occur. Okay. So what happens when the node split occurs? The middle value, it becomes the new root, and the first value becomes its left child because it is less than that. Okay. And the next value which is inserted becomes the child of it. This is how exactly we do the B trees also. But in the B plus tree, this plus information is something extra, which tells that the root value or the key has to be stored inside the leaf node. Okay. And they should be linked with the linked list fashion. So the siblings are connected with each other. This is the difference between the B trees and the B plus tree. This is the extra piece of information. This root being transferred in the leaf. So the value in the root is also stored inside the leaf. and they are all in ascending order. If you see 10, 20, 30, 40, exactly. Is this B? Now, this is the B tree after, resulting after inserting three values. Okay, now let's insert 40. Now, when we try to insert 40, 40 is greater than the root value, so it will come into the right subtree. Now, this is going to make the second node overflow, so the node will split. When the node will split, what happens? The middle value will become the root. Okay, so this root is pushed up at the level above it. And here we actually have one space, one key that can be accommodated, because my node should have how many values? Two values. Every node can have two values, including the root node. So here, this is how the resulting tree will look like: 20 and 30. Okay. 20's left child, 30's left child will be 20. Okay, I'm talking about this 20. And the right child will be how much? 40. And also 30 can be stored here, because 30 is the root node. It has to be inside the leaf node. And in the left child of 20, we have 10. They all are now connected in the linked list format. Okay, so now let's insert 50. Okay, 50 is again going to create a node split in, but here the node split is in two places. Okay, so here I have 50, and here, from here, the middle value will be sent up. Okay, and then here also there is a node split. The middle value will be sent up. So the new root here is going to be 30. Its left child will be 20 and 40, and so on. So let's do this. So after inserting 50, now we have two levels of node split, one in the leaf node and one in the internal node, and the new node comes into picture. And now what is the new thing? This 30 is now our new root. Okay, so we have 30. Okay, so we have 30 here, 30 as the new root. Okay, and we have 20. And then what happens? 30 became the new root, and this one will become the right child of 30. So we have here 40. Here we have 40. Once again. Okay. We have 40 here. 40 here. 40's left child will be now 30. And right child will be 50. But because we want to store the key also in the leaf node, the internal, the root nodes, root value, the parent value in the leaf node. So we have 40 here. And 20's right child will be 20. And the left child will be 10. Okay. So this is how the tree now looks like after inserting 50. Now we have to insert 60. This insertion of 60 is simple because there is only one node split. Okay, so this is 60. So 50 will be pushed up, and here we have a space for it. So, okay. We have 50 here. Okay. And now what will happen? Only these things will change. So let me make the space here. Okay. Okay. So now 50's left child will be 40. Okay. And right child will be 60. And we can store 50 here. Now, if you see all the values are in the leaf node. Okay. And they are all arranged. So now, now the next value what we want to insert is 70. Now 70 is going to split the node at two levels. So we have 70 here. The middle value will be pushed here. Oh, no, okay. The middle value will be pushed here. The middle value is 60. And then from here, in this node, there is again a node split, node overflow. So middle value is pushed here. So we have 50 going to come here. Okay. Now let's redraw this all. Let me have one more page. Insert page break. I want to have a page break here. So I have, okay, let me draw it here, no worries. So we were trying to insert 70. Okay, we were trying to insert 70. So we have 60 coming here and 50 coming here. Okay. Now, what will happen here now? 30. This is our root node, and it will get what? It will get 50 beside it. So I'm going to write 50 beside 30. So 50 beside 30. Okay. Okay, now let's write down the left child of 30 is going to be same 20, and right child of this is 10, and left child of this is again 20. Okay, the middle child is going to be 40. The middle child is going to be 40. 40's left child will be 30, and right child will be, because we have to store this value, 40 only. Okay, and then we have to the right of it. Okay, what do we have in the right of it? Right of it is having 60. Okay, and 50 of its, and then we're going to have to the right of it yeah, 70 and 60 can be stored here. Okay, now here actually 1 second, draw this 50. Okay. So here it is, right child is 60, right? Right child is 60. So it can have its left child as 50. Okay. Why am I not putting 50 here? Because 60 is greater than 50. Okay. And then it can have 50 as its left child. For example, here 40 and 30, 10, 20 and 10. And they all are linked together. Okay. They all have linked list. Okay. Now they all are linked together. 60 and 70. Okay. Now let's try to insert 80. 80 will cause the node split in this leaf node. Okay, and then it will push 70 as the parent. And here we can have the 70, right? Because this is the node and it can hold two values. So this is okay. So what are we going to do is we're just going to redraw it in this place. So this is gone now. And here we have 70. Okay, 70's left child is going to be 60 and right child is going to be 80, and also 70 can be stored here because the parent key is stored inside the leaf node. Okay, so now this is how we have the B tree looking after inserting 10, 20, 30, 40, 50, 60, 70, and 80. Now let's insert 90. Okay, now when we try to insert 90, there is a node split here, and there will be a node split here also. And there will be a node split here also. Okay, so uh, here 90, and here what is the value? Middle value 80. And here what is the middle value? 70. And here what is the middle value? 50. So 50 is going to be our new root now. So let's draw 50. Okay. And we have what is the what is the value before 50 will become the left child. So we have here 30. What is the value after 50? 70. 70 will become the right child. 70 will become the right child. Okay. Now, now we have to do this. Okay. So, the left child is going to be how much? 20. Okay. And its right child is going to be how much? Right child is going to be 40. Okay. From here. And 40's left child is 30. Okay. And 20's right child is how much? 20. And the right child, left child is how much? 10. Left child is 10. Okay. So, and here the right child will be 40. Okay. And then 70's left child. Oh, where is 70? 70's left child is 60. So left child is 60. Okay. And 60, where 60 is here. And who is its left child? 50. So I am putting 50 here. Okay. And what is the right child of 60? 60 only. So this is going to be 60. Okay, so far so good. Now let's talk about the right child of 70 is going to be 80 now. So we have here 80. Okay, to the left of 80, what do we have? 70. So we have 70 here. Okay, to the right of 80, what do we have? To the right of 80 is this new value. Okay, so we have value here 90 and also 80 can be stored here. They all are connected in the linked list format. Linked list format. Okay. Now this is how the B plus tree looks like after inserting 9 values. Now let us insert 100 value, which is the last value in our case. Okay. So 100 will come here because it is greater than root, so it has to come to the rightmost in this case, right? It is greater than all the values in the right tree. So I am going to write 100 here. Node split will happen. And then one more node split. No, is there a need to have a node split here? No, because it has already the space to accommodate one more key. So here, simple thing, 90 will go here. And the node is not, in this case, only the node will split. So here we have only one change. And what is that change? 90's left child will be 80. Okay. And the right child will be 100. And also 90 can be stored here. So now we have this 10, 20, 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And we have all the nodes arranged. Okay. So, yeah, if you check at the root, we have 50 here. At the root, we have 50, then 30 and 70, 30 and 70. And then we have 20, 40, 60, 80, 90. 20, 40, 60, 80, 90, and then all these values. So this is the B plus tree trying to insert 10 values with the order of 3. In this example, the values, I took it in the ascending order because I just wanted you to understand the insertion process. However, they can be jumbled values, okay, unsorted. In this case, the left tree will also grow. Okay, in this case, the left tree will also grow and the right tree will also grow, but the concept is same. So in order to make it simple, I have concentrated on just increasing the right tree, right subtree, and you know, balancing it in the left side. However, you can have different values, and many examples are, one more example is given here. We have value as 8, 5, 1, 7, 3, 12, 9, 6. Okay. And the order of the tree is 3, and we can have maximum 2 values, and then it keeps on growing. Okay. So this is an example of inserting the keys inside the B plus tree. Now let's discuss the deletion of an element from a B plus tree. The deletion of an element from a B plus tree might arise a situation wherein we try to keep on deleting the node values, and as a result, the node might get underflow. In the insertion, we have seen that when the node capacity is reached after inserting new values inside it, the node split occurs, and then the middle element is created as a root, and the left and right elements becomes the left and right child, and then the whole tree is reconstructed. However, in B plus tree element deletion, the case is opposite. Here, while deleting the keys out of a node might result in a situation called as node underflow. The node underflow occurs when the number of keys inside a node falls than the minimum required keys. And how do we have to find out the minimum required elements or the keys inside the given node? We use a formula which is called as P. I want to uh, draw. I just want to let me select the color. Yes. And then pen. Yes. Yeah. We find out the minimum required keys inside a node with a formula called as P divided by 2. Apply the ceil function to it, and then -1. So we know that the order of the tree gives us the value of P. So if the order of the P is 3, it means the order of the tree is going to be 3, and minimum it can have 3 divided by 2, apply the ceil function to it, and -1. So in this case, it is going to have one value as a minimum value, and maximum it can have two values. 3 minus 1 is 2. Similarly, the minimum number of children is going to be the order of the P divided by 2, and apply the ceil function. So in this case, 3 divided by 2 is like 1.5, and then apply the ceil function, it becomes 2. It means it can have 2 children. It can have 2 children. Okay, when the order of the tree, 2 children, it can have 2 children. Okay, when the order of the tree is 3 maximum. Okay, and it can have uh, maximum 3 children. Minimum 2, maximum it can have 2 key values, and minimum it can have 1 value as per our formula. Okay, now there could be 3 situations wherein we would try to delete an element. The key might be present in the leaf node, or the key might be present in the internal node but not in the root node. And the third case is when the key is present in the root node. These can be, there can be one of the situation from where we might be required to delete the key. Okay, the key can be in the leaf node. Okay, and the tree can be the non root node. but it is not the leaf node, which means it is an internal node. And the key is in the root node. Okay, so these are the three situations that can arise. The solution to this can be either by redistributing, okay, or it can be by borrowing or merging the nodes. Okay, so using these, approaches, we can handle the deletion. Now, it is very important to understand that the results that come from deletion of the values may get, propagated up the tree, and the level of the tree can also decrease. The level of the tree can also decrease. The height of the tree can also reduce, and the levels of the tree can also reduce. Now, let us look at into the first situation. When you are trying to delete a key which is kept in the leaf node, okay, look at this condition. If this condition is not yet reached, if this condition is not yet reached, then you are safe to delete a key without making the merge or borrow or the redistribution. How do we do that? For example, if we have the tree, okay, with the order of order is 3, okay, and minimum, how many values can I have? Maximum 2 values I can have, minimum 1 value I can have. Okay, now if it means that if any of the leaf node is having 2 values, I can just delete 1 value without disturbing any other leaves, without redistributing or merging or without borrowing. Okay, now let's see how is that done. For a key in a leaf node, okay, we want to delete it, just delete it. Ensure the node occupancy rule. What is the node occupancy rule? This is the node occupancy rule. By redistributing the keys among the edges. And now, if this rule is now, if this rule is taken care, or if this rule is not broken, then you just delete and forget about it. For example, here in this example, we have the root node 7, and then in the left child, we have 1 and 6. And to the left of 1, we have 1. And then in the middle of this 1 and 6, there is 5 and 6 elements. And then to the right, we have 7. Now we are trying to delete the element 5. We are trying to delete the element 5. Let me take the pen, please. We are trying to delete, why that's not right. So it means when we try, no, okay. We have to, okay. So when I'm trying to delete the number 5 from here, okay, I know that minimum, this node can hold 2 values, okay. Minimum it can hold, sorry, minimum it can have 1 value, and it is having maximum 2 values inside it. So if I just delete it, it is not going to disturb. I don't need to borrow. I don't need to merge. So this is the simplest case. Just check that if the node have the maximum values inside it, and you are supposed to delete one element from one key from it, then just delete it. And this is a simple deletion. We don't have to check for redistributing or merging to restore the tree balance, because the node is not underflowing. If and only if there is an underflow, then only we use one of this solution, borrowing or merging or redistributing. Okay, in this case it is simple, nothing, we just delete it. Okay, for now, let's see in another case what happens in another case. The key is inside the leaf node, okay, but after deleting the key, the node will underflow, meaning that it is going to have no values inside the node in our case, because the order of the tree is 3. Maximum it can have 2 values, and minimum it can have 1 value. Now, if I'm trying to delete this 1 value also, what will happen? The node will become empty. When it is empty, it is called as underflow. Now, in this case, what we have to do is we have to borrow the tree. For example, now let's look at the situation. We just deleted the 5, okay, element. Now we are trying to delete 12. Now we are trying to delete 12, right? So When we try to delete this 12, the node will become empty. Okay, now you see the node will become empty. So this box will be empty and it is going to be underflow. So what are we going to do? We are going to redistribute. We are going to redistribute the keys among the adjacent nodes. So what happens now? Let's see the solution here. Let's see the solution here. What did we do? We deleted 2 from here. This became empty. Okay. Now we are seeing we are trying to borrow the keys from the left, okay, and left sibling is having 2 keys, and the left tree can have the same value, okay, and the second variant of the first case could be that we have a leaf node, okay, but deleting the leaf node is causing an underflow. For example, we are trying to delete the number 12. Here, this element is the single element present in this node. Now, if we delete this element, this node will become empty and the node will underflow. In this case, what we have to do is we have to redistribute. We check if the sibling is having extra than the minimum required keys. Yes, in this case, a minimum it should have 1 key, and this node is having 2 keys. So we can borrow from the left child or the left sibling, sorry, and then the 9 will be moved here. When we move 9, okay, actually, we are moving through the root. So the 9 comes here and then the 8 is placed in the root. So this case is called as underflow case with the leaf node and we redistribute. Okay. So the second case is we are trying to delete the internal node, but that internal node is not the root node. It is something like we are trying to delete 6. Okay. In this case, what we have to do is, in the case of deleting a key from the non-root internal node, we are going to take the smallest value from the right subtree or the largest value from the left subtree. Okay, for example, if we are trying to delete the 6, then
from the left subtree, we can take the highest value, or from the right subtree, we can take the max value. Okay. Update the key recursively, delete it from the appropriate child, and maintain the node balancing factor. Third could be the case wherein we want to delete the root itself, for example, 7. Now, when we delete the root and the root becomes empty, then we are going to again take the smallest key from the right subtree, or and then designating this as a new root, and adjust the tree height. Yeah, when you delete the root, actually you are decreasing the levels in the B plus tree. So the height will reduce, the levels will reduce, and then the smallest key from the right subtree. Okay. For example, here we try to delete 7, then we go to the right of it 9, and then we take the smallest keys. So 8 will be placed here. Okay. So this is how the three cases exist while we are trying to delete from the B plus tree. We have an example given here. The order of the tree is 3. Minimum values or the keys node can have is 1. If we try to delete this single element, then the underflow will occur, and we have to check if the right sibling or the left sibling are having, if the right or the left sibling is having more than one key, we can borrow one and then redistribute. If that is not the case, for example, we are trying to delete 9 from here, and then the left sibling is also 8, a single one. So if we delete 9, this will underflow, this node will underflow, and also it cannot borrow from the left sibling. So what we have to do is, in this case, we delete 9, we merge 8 and the empty node, and then we delete this 8 and we shift 7 from here. So it's like this is getting empty. Okay, let me take a pen and then draw for you. So highlight her pen. Yes. So when we delete this 9, okay, what will happen? This will become empty, but it cannot borrow. So we have to merge. So we have to merge this and this. Okay, we need to merge this and this. When we need to merge this and put it here, okay, so we have to redistribute it, because you see, this is the node, root node, which is going to help in the redistribution. So what will happen? 6 will go here, okay, and 7 will come here. So you see, 6 is here and 7 is here, okay, and then 7 is having left child as 7 itself and right child as 8. Now this becomes the proper distribution. So uh, okay, so let me explain you the different cases here. Okay, so I want to remove with the eraser. This problem tells so it has been asked in the midterm exams that given the set of numbers to be removed from the B plus tree, and the tree structure is given to you. In this case, we want to delete 5, 12, and 9. Okay, deleting 5 is simple. Okay, because it is in the leaf node, and we have 2 keys, which is like 1 extra than the minimum required. So we just delete it without bothering. So this deletion is simple. We just delete it and it becomes empty. The second one is 12. We search 12 is greater than 7, greater than 9. We come to the right subtree. Okay, and then here we locate the number 12. Okay, now deleting here will cause the underflow at this particular node. So redistribute. Redistribute is only possible when your left or right subnodes have more than extra minimum required keys, more than minimum required keys. So yeah, this minimum is 1, because the order of the tree is 3 here. So minimum keys is 1, maximum keys are 2. So it is having maximum keys actually. So it can give you 1 key to this empty node. So what happens? But this has to go through the root. So 9 is shifted here. Okay, this 9, because when we are borrowing it from the left tree, left sibling, we take the highest value. So 9 has to be kept here, but it cannot directly give. So it goes to the root, and from the root it comes here. And this is how the merge redistribution is being performed. Okay, so yeah, done. Now what's happening if you have 9 here and 9 here, okay, then it's like moving directly. So what we do is we have to move this 8 to the root, and then we move 9 here. So now we have 9, 8. Now this looks a proper B plus tree, 8, and then its right tree is 9 greater than it, and the left is 8. Okay, so we have this. This is underflow. Okay, now when this is underflow with redistribute. Now we want to delete 9, and its left sibling is also having a minimum required value. So it cannot give you this extra value, right? So what we have to do is we have to merge 8 and this empty node so that they become one node. Okay, when we do that, what we do is we have to, 8 cannot have 8 as the right child, right? And then this is also going to be deleted, and this is also going to be deleted. Here we will have only 8, so 8 cannot have only 8. It need to have another children, because another child also, right? Because maximum 3 children it can have, or minimum it need to have 2 children. So there is no, there is an one empty child here. There is no child actually. So what we have to do is we have to redistribute at this level. Now when we redistribute, what we do is we bring 7 here in this place. Okay, you see 7 here, and then this is the right child, and this is the left child. Okay, we bring 7 here, and this becomes empty. So what we do is here we have two values. One value is now shifted to the root. Okay, so underflow can be sorted or solved by redistributing, or underflow can be sorted and solved by merge. Okay, now what are the cases that how do you know that when to use merge and when to use redistribute? How do you decide? Yeah, you decide based on the number of elements inside the sibling. Okay, now here underflow is happening. The left sibling is having two values. One can be given. Okay, how do you give this one? You pass this 9 here, okay, and this becomes 8. So you move 8 here and 9 here. Okay, so you change, it's like 8 going here, 9 coming here. Okay, so this is called as redistribute. This is actually what we did also here, right? We move 6 here and we move 7 here. So it's like 6 here and 7 here. And this is how the redistribution works. Okay, now when to do the merging. Merging is done when we fall short of children for a particular node after becoming it empty. For example, in this case, when you delete 9, when you are going to delete 9, you are going to make the node empty. Okay, you are going to make this node empty. Now, when this is empty, it will be deleted for sure. So what you do is you merge this and this. In this case, what will happen? 8 will have 8 as a right child, which is not correct according to the B+Tree. The right child should be greater than the parent node. So what will happen? We merge and we delete this 8. When the merging of two leaf nodes are occurring, we merge the leaf node value 8, and in this case the empty value together, and then we delete this 8. And in this place, what will happen? Then you redistribute. So 6 here in this node, we have two values. So one can be promoted to become the new node, root node, and this root node will come here. Okay, and then it will have one child as 7 and another child as 8. So in this case, the minimum number of children for this node are 2. Okay, okay. And for this node, there are 2 children. Okay, satisfied. Okay, for this node, we have 2 children, again satisfied. Okay, and each node can have a single value. Okay, minimum value is single. So we have that. Okay, so this is how the deletion is done. Now, what I want you to do is, given this B plus tree, okay, try to delete 21, reconstruct the 3, 31, and write down what is the change after deleting 31, and keep on deleting, okay, all these given values, and then solve the complete tree. And in this case, you will come across the first case, second case, third case, all the cases are there. Okay, so if you want to refer, this is a very good video. You can refer to this video to solve this, and then you're going to upload it in the Blackboard. Okay, this is what all about. This is all about the uh, uh, B plus tree deletion. Okay, very important. I have been asked many times in the midterm exam. Thank you.